Hello, my name is Krish Thakre, and today I will be presenting my procedure for designing, planning, and constructing a bridge concept and a scale model in order to solve an ongoing problem in society. So what is that problem that's being faced? Well, throughout recent history, we have unfortunately seen a multitude of sudden, devastating collapses or failures of occupied roadway bridges, and these catastrophic events have ended up hurting and killing hundreds of people. There are many examples of flawed approaches to engineering and designing bridges that have cost many lives, such as the bridge in the top right image, which crumbled in Minnesota in 2007 due to faulty gusset plates. So it was our goal to design a concept bridge that learned from the occurrences of these failures in order to achieve a high structural integrity, efficiency, and reliability even under the stresses of vehicles traveling atop it. And to construct our bridge prototype, which would be done after completing the concept generation and online designing phases, we were to utilize long and thin sticks of balsa wood and cut them into pieces that would fit together using wood glue to form the framework of our bridge according to the following criteria. On the framework, we were to place a balsa wood sheet roadbed with a hole in the center for destructive testing. And for this test, our goal was to make sure our bridge would hold up at least 15 pounds. And here are a few terminologies during the design process and the research process that were especially vital to my understanding of bridge design. Particularly, understanding the roles of the superstructure and substructure was incredibly important to make sure that I could be more productive when working with my teammate in order to design our bridge. And here is the bridge design that we finalized and selected out of our 4 original options. It's called a Pratt truss bridge, and it's well known for its ability to support automobiles driving over it in a versatile and functional manner. We also selected this style because of its high efficiency, as it requires less components for structural integrity and stability while also keeping parts standardized. And also, as you can see here, this is our digital representation of our concept bridge, which we built using Onshape, a type of computer-aided design software. We also used this digital build to create multi-view 1-to-1 scale drawings on which we would build the faces of our bridge in a tracing manner, as you will see in the next slide. So in order to construct our prototype, we cut the aforementioned wooden beams into diagonally and straight cut shorter beams that could be placed face to face or edge to edge and coated with glue in order to ensure a secure binding. We glued these components in an orderly fashion in order to ensure that the glue dried appropriately. And here you can see what I was talking about with the tracing, as we laid each piece on top of the side view or even the bottom view with regards to the bridge deck support in order to make sure that we got all the shaping and all the angles correct. So after the glue had been reliably dried, test day had arrived and we were to put our bridge to the test atop a gradual weight application device. We went in between groups of other students constructing their own bridge prototypes, and as such, we collected data on all of them to make an accurate comparison of our bridge's performance. And at the end of it, our bridge's max load soared well past the 15-pound mark and went up to 32 pounds before cracks were heard in the bridge support, and the weight could not increase anymore. Upon inspection, damages were not entirely visible, and the bridge's overall integrity was sustained with the exception of the 2 horizontal straight cut beams on the ends of the deck support, which had cracked. So our bridge's high maximum load and overall success has proven to be a testament to the strength of the diagonal bracing and beams that we laid within the deck support horizontally, as well as the overall greater amount of straight cut horizontal beams throughout the substructure and superstructure that aided in dissipating the forces even more. Our team's success can also be attributed to the strength and reliability of the Pratt truss bridge design, and not to mention the high efficiency meant that we were able to complete construction well before the deadline despite taking more time on prior steps. And some improvements, though, that could be made would be to add even more diagonal horizontal beams on the far end of the deck support structure in order to dissipate some force away from, as mentioned before, the horizontal straight cut beams that cracked during the process of destructive testing in order to allow for even more headroom when adding weight to the bridge. And overall, this project went quite well, as a combination of teamwork and following the engineering design process proved to generate overall very promising results. Thank you for watching this presentation.